No, I think it's a pretty strict.
Of course. Welcome everybody. In this afternoon lectures, we will be looking at newer topics, and it's a pleasure to introduce David Steurer, who's at Cornell University, visiting for the whole semester. So he'll be here for the whole semester, and he'll be telling us about sum of squares, SDP relaxations, and their applications to approximation algorithms, or even machine learning applications. And let David start.
Thanks, Prasad. Thanks for inviting me. Okay, so the motivation. So I want to start with some motivation. So we'll be trying to solve optimization problems. And like most of the discussion is very general, and I'll have some examples. And so the kind of optimization problem that we are interested in are following form. So we have some function that we want to maximize, and we have some properties that we want of the solutions, encoded by these kind of equations. And the solution is encoded as a real vector. And here we are thinking of n as very large. So we have many variables. And in the sense that we will also measure. Yes? Larger? Okay. We will measure the running time of the algorithms in terms of the number of variables. Again, if you sort of talk about real valued, a function on real vectors, and we have to somehow say how we encode these functions. And the way we will do this is that the functions p0, p1 to pm are low degree polynomials. It could be degree 2 or degree 4. So really just a constant degree, and we also, the number of constraints will be small, and coefficients will be small. So that's the basic setup, and an example of a problem that, and this is a very expressive way of describing optimization problems. An example of a problem, how you can describe a problem in this way is, let's say, for the maximum cut in a graph. A little bit larger. Graph G with n vertices. Okay, so how could we? So we want to find it by partition. We want to find it by partition of the vertex set of the graph, such that the number of edges that cross the bipartition is as large as possible. So how can we encode it in this way? So the main step is to sort of encode the solutions real vectors. In the sort of equivalent ways of doing it, maybe a simple thing is that we think of we have a variable for every vertex I. We have a variable x sub I, and a coordinate of a vector, and we assign 1 to all the vertices on one side of the cut, and -1 to all the vertices on the other side of the cut, and then we want to formulate we want to sort of express the condition that we want to maximize the number of edges that that the bipartition cuts in terms of some function P0. So P0 of x should be the number of edges that cross the bipartition x, and this function you can interpolate it as a polynomial in these variables, and then it has this form. So here we sum up over the edges of the graph these squares, and you see that they just count the number of edges that cross the bipartition. And so this is the Laplacian of the graph, which you've seen in Luca's talk. Okay, and so we're lucky that this polynomial is indeed a low degree polynomial. So this fits into what we said before.
So here you also say that all x is squared over 1.
Yes, okay, so a good point. So yes, I think that's what maybe I should take the notes. Right. So what we did here is we every bipartition we associated with some vector x with plus one minus one coordinates, and now we want we have this. We have to specify the constraints here, and so the way we choose P1 up to Pm, the way we want to choose these polynomials is we choose this as a good basis. Of polynomials that are zero over the set that we're interested in. And good basis can mean different things depending on exactly what problem you're looking at. Here it's sort of clear what's the basis that you want. So you choose the following polynomials, just x1 squared minus 1 up to xn squared minus 1. So the condition that those polynomials are zero says that the vector x is plus or minus 1 coordinates. Okay. And okay, so this is the basic setup. Now, the question that we're interested in is, are there efficient algorithms for these kind of problems? And as you probably know, this problem is NP-hard. Let's say, let's even talk. Let's keep this example of max cut. So the efficient algorithm. So this problem is NP-hard to solve exactly. And even in the sense that, so the proof, the hardness proof even shows that if you want to solve it exactly, it requires under some reasonable assumptions exponential time. And now, so it means that the real question is that how close can you get? And there's basic results. P theorem says that sort of some kind of 0.99 approximation is as hard as solving the problem exactly. Okay, here I should also say I'm not sure if you remember it from Luca's talk. How we measure approximation. So usually you have to, you might have to measure it depending on the problem, but so in this case, some alpha approximation means that the solution found by the algorithm on a particular input graph G is at least alpha times the optimum, the value of the optimum solution for the graph G, and this is for all graphs G.
Not for max cut.
Again?
For max cut, it's always winners.
So here I'm
Oh, you're referring to the...
so this is the hardness result. So this is this that even 0.99 approximation requires exponential time. Okay. And right, and then there's this and there are better ones known, but for hardness results, but let me not say them. And then there's this the best known algorithm, 0.878 approximation. Polynomial time, and actually nearly linear time. And assuming the Games conjecture, implies that it's NP-hard. Better approximation is NP-hard. And okay, and we don't know if the Games conjecture is true, and in some sense that's finding out whether the Games conjecture is true is one of the motivations of the things I'm talking about. Now you might wonder, okay, why do we really care about the difference between 0.99, 0.878? So I think maybe one reason why you want to care about this is that here, you're maybe not interested just in the numerical value, but you want to know, what's the algorithm that that achieves the best possible approximation. And if you look at this, then here the algorithm that achieves 0.878. This is based on let me call it degree 2 semidefinite programming. again, this is sort of not a very technical expression, just put in quotes. And now sort of something interesting happens. For example, it's open what, so there's, just like there's degree 2 semi-definite programming, there are, it's open whether there are higher degree versions of semi-definite programming, and so you can look at degree 4 semi-definite programming, and this is, it's open whether this gives a strictly better approximation. And if it would be the case, that would refute this Unigans conjecture. In some sense, our inability to show that this version of semi-definite programming does not refute the Unigans conjecture explains why we are not super confident in the truth of the Unigans conjecture. Okay. And it's even a bit worse. So it's not just open that whether this degree 4 achieves a better approximation, but so we know a bit more. Okay. So every known, again some restriction, tight, bad example for degree 2, is provably, not a bad example for degree 16. Okay, and 16 is sort of somewhat arbitrary number. Okay, so and here, every known, so the restriction is known to me. But so it means that for every particular construction of graphs where where we know that, or that where the degree 2 where this guarantee for degree 2 is tight, you can actually show that degree 16 is much better. Okay, and this is maybe somewhat surprising, especially. So it means that if the Unigans conjecture is true, then degree 16 should not give a better approximation for this problem, and so it means that there have to be different instances.
The degree is the degree of the polynomials over here. What's when you say degree 2?
Yes, good question. So here, so there are two degrees at play. One is the degree that you need to specify the problem, and for Maxcart this is degree 2. And to some extent, you can, degree 2 is always enough to define at least sort of combinatorial kind of problems. And then there is the degree that you use for the algorithm, and those degrees are you can choose a degree for the algorithm larger, and that's that turns out to help for these bad instances. Yeah. But so far I didn't explain exactly what degree 16 semi-definite programming means, but I will do that. Okay, and so the conclusion of this kind of discussion is that the goal here is what we'd like to have is some kind of unified. So we have so this is really just some kind of some particular example, this Maxcart, and so there are a lot of problems of different kinds where we, that have this form, this kind of optimization problems, and where we'd like to understand what are the best possible algorithms, and so the goal is to have some kind of unified way of attacking these problems. We're approaching these problems. And in the sense that this, should apply to other combinatorial optimization problems. And other kind of problems where these kind of techniques seem to be useful are certain unsupervised learning problems. Like sort of related to sparsity, tensors, and matrix factorization kind of things. Okay. And this unified way of approaching these problems is in terms of convex relaxations. And so that's the main topic of the lecture today. So the basic idea is that we have these problems, and we try to and there's the sense that convex optimization is easy, and so the idea is to reduce these arbitrary optimization problems to convex optimization problems, and then hope that in this way we get good algorithms. And so there are different ways of doing this, and so what I will explain is sort of some kind of way of looking at these convex relaxations that is fairly unified. And so the first one thing that we need to do is we need to convexify the problem. And so it means that we want to make the problem into a convex problem. A convex problem means that you can take convex combinations of solutions and get solutions that are at least as good. So if you have a bunch of good solutions and you take a convex combination, then and you want to have another good solution. And and there's a sort of canonical way to make every problem convex. So what's this? How can you do this? Instead of just trying to find a particular solution, what you try to do is you try to find a distribution over solutions. And D is what do I want to do? Okay, so let me keep this example of max cut. Will make things a little bit easier. So that's how do you convexify max cut? And here is you want to find a distribution D. This probability distribution over the hypercube, and you want to maximize the expectation of the polynomial that you're interested in, with respect to this distribution. Okay, and so what did we gain? We gained a couple of things. So maybe let me just explain what is a distribution. So a distribution is a function on the hypercube, a real-valued function, and it has the property that for every point in the hypercube, it takes a non-negative value, and if you sum up the values of all points in the hypercube, then you get 1. Okay. And okay, so that's a distribution. What we gain? So one thing is that we gained is that here now this objective function is linear indeed. Okay. Another thing that we gained is that now the problem is convex in the sense that if you take two distributions over the hypercube G and D prime, and you take a convex combination in this sense, think of it as a function, then this is again is a distribution. if D and D prime are distributions. Okay. And so the only problem here is, so maybe there are two problems. One problem is, okay, so this object here is exponentially large. This is actually not the main problem. The main problem here is that we have here an exponential number of inequalities. And these inequalities are sort of not structured in a way that would allow to deal with them in an efficient way. And so that's the main problem. And let me also say that instead of finding a distribution and maximizing the expectation of the polynomial you want to, of the function that you want to maximize, it's in some sense a bit better. Okay, where should I write this? Let me write this down here. It's a bit better to, in some situations, to think of. You want to find a distribution over the set, of all optimal solutions. Where C is some guess for the optimal value. Okay, so meaning that instead of finding so by convexifying, I mean that instead of finding a particular solution, what you try to do is to find distribution over solutions. Okay. And a priori, this doesn't make things easier. So in particular, this problem is computationally at least as hard, but what you gain is that it gives you sort of a new perspective on the problem, and in particular now we will relax the problem, we make the problem easier, and so some of you want to keep the property that things are convex, because then we can use convex optimization techniques. But we somehow want to simplify the problem so that we can solve things efficiently. And there are many ways of sort of explaining how this goes. But I think particular a very general way and convenient way to deal with these things is in terms of pseudo distributions. Okay, so what is pseudo distribution? So short way to think about it is that it behaves like a probability distribution. Distribution over, let's say, optimal solutions. So it means, in terms of, in the case of max cut, over optimal cuts in the graph. And it behaves as this kind of object with respect to our computational knowledge. About optimal solutions. So this computational knowledge is something that I will define in a bit. So there's a sense in which you can think about what do you actually know about optimal solutions, and then you can think about what it means to have something like a distribution something that behaves like a distribution with respect to this knowledge. Okay. And then, so once we have this, the general approach will be find a pseudo distribution efficiently, and then extract a good solution. It might not be an optimal solution, but the goal is to still be able to get a good solution from this pseudo distribution. There will be some loss here, which will determine the approximation factor. Okay, so this is the general idea, and here, there are different ways of thinking about this step. This is sometimes called rounding. Another way is related. It's also related to polymorphisms, and we are calling it sometimes combining. And it will be clearer later in later lectures about how to think about this process. Okay, so now what is this computational knowledge? Go back here.
Before you say with pseudo distributions, to say why you can do with once you've transformed the pseudo distributions, things are efficient, whereas they weren't before. What's the change?
Yes. So because we don't want them to be exactly probability distributions, but only with respect to what we know about the problem. So that means that it's easier to find these kind of objects than actual probability distributions, and the algorithms that will find these pseudo distributions, they are convex optimization problems. So it turns out that this will be finding a pseudo distribution will be a convex optimization problem. Which is not surprising because finding actual distributions is also a convex optimization problem. But here this will be a small convex optimization problem. So now, so what is computational knowledge? So let's first start with what is knowledge about optimal solutions? So it's just a set of functions that has a property that if f is a function in the set, it implies that f of x is non-negative for every optimal solution for every solution x of value c, where c was our guess for the optimal value. And this is also something that you can always make. That you can guess what's the optimal value, and then just try to see if you can find a distribution for that particular value c. Now, so this is just a bunch of inequalities that you know about optimal solutions. Okay? And now, what does it mean to have a pseudo distribution that is consistent? D is consistent with some particular knowledge K. So this just means that for every function that we know to be non-negative, that we know to be non-negative over on optimal solutions, we want that the following expression is non-negative. Okay, maybe let me. Okay, the following expression is non-negative. sum over all points in the hypercube. Some kind of inner product between the function d and the function f. And the other condition is that if you sum up the values of d, then you get 1. Okay? So it means that we replace the condition that d is non-negative everywhere by the condition that by this strange condition. Okay, so and it sort of gets old to sort of write these sums, and therefore we will give this a name and a notation. So we'll denote it in this way. So sorry, maybe I should clearer here. So this summation for any function f we will denote it in this way, and we will refer to it as the pseudo expectation. Of f, yes?
Will there be examples where the knowledge uses the optimal value c?
That's a good question. Maybe not today, but so there are some cases where things become much more pleasant if you know if you use the value c.
So pseudo expectation differs from an expectation because d could be positive or negative?
Yes, exactly. So that's what we dropped. So we no longer require that d is non-negative everywhere. But we keep the condition that d sums up to 1, and instead of non-negativity everywhere, we just require that these pseudo expectations are non-negative for functions that we know to be non-negative on optimal solutions. Okay, and now, yes.
So, in like a lot of the examples, f is low degree.
Yes.
But, are there examples where f is already need a high degree f?
It's also a good question. Yeah, I don't know of an example where high degree f is needed. Yeah, but that's so that's also an important point. So somehow, like clearly not, so we have to, so the question is, when can we argue about consistency with respect to some particular set of functions k? When can we deal with this efficiently? And clearly, we can't do it for some set of functions, it's not possible to do it efficiently. So, for example, if k consists of, another example, so if we choose our knowledge to be, all the set of, singleton indicators. For every point x, we have a function in k which is 1 exactly at this point x and 0 everywhere else. So we can look at this or let's say that is just 1 at every for every solution x that has value c. So if you had the indicator of every such solution in our set k, then it means that
Then d needs to be distribution.
Yes. Then pseudo distribution with respect to that set k is an actual distribution. It's an actual distribution. That means that we somehow have to restrict the set of functions k, and that's what I meant that we that we only get a pseudo distribution that is consistent with respect to our computational knowledge. And so this means that there exists, so there's some parameter d, so there exists an n to the d time algorithm that can solve the following problem. given f, given a function d, sorry, compute the function our knowledge that minimizes, that has smallest pseudo expectation. So for every function d, you want to be able to compute. Sorry. Given d, you want to compute. The function in K that minimizes this pseudo expectation. A different way of thinking about it is that given some function d, you want to be able to tell whether whether it's consistent with the knowledge K, in the sense that that all these pseudo expectations are non-negative, and if d is not consistent with the knowledge K, then you want to find some function f that is where the pseudo expectation is negative.
It's the definition of computational knowledge.
Say again?
It's the definition of computational knowledge.
So that there exists an end-to-the-d-time algorithm that can solve the following problem. Given a function d, compute the function f that minimizes this expectation.
So for every value of little d, you have a different set of computational knowledge.
Yes. I mean,
how are you given the big D?
say again?
What does it mean for D to be given?
Given, yeah, okay, that's also a good question. What is d? Yes, I think maybe I should have, yes, I think, no, right, so here, a priori d, is a function on 2 to the n points, so that, that's much larger than the time the algorithm has. So you somehow have to represent d in a good way. And here, that's goes back to Madur's point. We will assume that we'll only look at the case where this set K contains only degree d polynomials. Where this d here is roughly the same as this d, contains only degree d polynomials. And why does it make? Why does this make things easier? This makes things easier because so now the set of functions that we care about, that we know to be non-negative, they are all degree d polynomials. And so it means that in this expression, the higher degree part of d, so for every function capital D, you can write it as a low degree part plus a high degree part. And the high degree part, it will not be able to contribute in this expression because f is a low degree polynomial. So the high degree part doesn't contribute here, and so it means that we can represent d by its low degree part. If our knowledge only contains low degree polynomials.
So that means you're looking at the moments up to the d moments.
Yes, that's right.
Okay.
So it means that sometimes the only thing that we know about, or the only thing that matters of this function capital D is its low degree moments. But in some sense, they are not actual moments because this function might take negative values sometimes, and so so I guess you could call these numbers pseudo moments. Yes.
Are there? So I know you said that we don't know of applications where high degree functions f are needed, but that notwithstanding, are there interesting classes of higher degree f for which we know how to solve this basically separation problem?
Okay, yes, that's a good question. Okay, so far I didn't specify exactly what. So that's what comes next. So next we will discuss sort of concrete examples of what what could be, how would the set K look like. So one case is that you just let K be some kind of cone generated by a small number of rays, by a polynomial number of rays, and then you can always then it's always possible to solve this problem efficiently. And I mean, yeah. So there is a sense in which you can, in which you don't need low degree polynomials if you want things to be efficient. But we don't know of an example where that's actually useful. That's also a great open question to show that like low degree things are the best. This is the only thing that you have to look at.
So you did this in some generality, but then at some point it didn't make sense anymore to say it's talk about things that were not low degree because you need some implicit representation for D. But you're saying if K is in some sense finite dimensional, then you also have a finite dimensional representation for D.
Yes.
Sorry, bounded dimensional.
Yes. Right. So that's right. So if okay, I think that's probably some kind of necessary condition that if you look at the affine span of K, the linear span of K, that this should not be too large. Otherwise, there's no hope. Otherwise, it cannot be computationally efficient in this sense. Okay, and yeah, so maybe let me sort of state the theorem, which is in some sense just restating the fact that convex problems you can solve them efficiently. If you have this, to state this, yes. So there exists, n to the d algorithm. That to find a pseudo distribution. D consistent with computation, if you have with some computational knowledge. Okay, and this is the same D here. And okay, maybe I should. So there's some constants which I'm not writing. And this is really just the observation that you can use this. That this problem that you have to solve here is sort of the separation problem for the. Is a separation problem for the pseudo distributions, and therefore using the ellipsoid method or your other favorite convex optimization algorithm, you can find a pseudo distribution that is consistent with some computational knowledge. Okay. So yeah, you can either think of this as a separation oracle or also as some kind of algorithm that computes the subgradient of the function that you want to minimize, or some function that you want to minimize. Okay, so now, now some examples. So one example is that you can use some kind of local knowledge, and this would be this would correspond to choosing K to be all non-negative combinations of non-negative D-juntas. Okay, so these kind of, so these are D-juntas over the hypercube. A D-junta is a function that depends only on at most D variables. Okay. So these are functions that they are not negative everywhere on the hypercube. So in particular, they satisfy this here. If you choose D to be very large, like n, then you will also have these. This set will also contain these indicators. That means that if you choose D to be n, then you actually talk about actual probability distributions. And another fact is that the number of rays here. So this here is a convex cone, and the number of rays is roughly 2 to the d times n choose d. And so it means that in this case you can just solve this problem by trying out every ray here, and that it takes time roughly n choose d, n to the d. Okay. And this here, if you use this kind of local knowledge, that is the resulting algorithm is called the Adams LP relaxation. Now another kind of knowledge that you can use is sum of squares knowledge. And here that would be all polynomials that are sums, all polynomials that are sum of squares of degree D polynomials. So these are also non-negative. So it means that you can do this. Also, if you choose degree D if you choose D to be very large, then you get these indicators, which means that you solve the problem exactly. Now, why is it computationally efficient? So, okay, so they have to look at this this kind of problem, and basically, so this problem becomes given some low degree polynomial D. So D is now, as we said here, low degree polynomial. You want to find the argmin of we sort of we are interested in squares of low degree polynomials. So we go over every low degree polynomial P, and we want to minimize the pseudo expectation. Find a polynomial P where this pseudo expectation is as small as possible. Okay. And now if you look at this here, this is a quadratic form in P. And so it means that minimizing that is just some eigenvalue kind of problem. So that's something that you can do efficiently.
This is your separation, right?
Yes, that would be the separation oracle. So the separation oracle for sum of squares knowledge would be an eigenvalue computation. Okay. Now, might be almost out of time. And so the point that I'd like to make here is that the sum of squares knowledge is surprisingly close to our real-world knowledge about low-degree polynomials. So if you give me sort of a concrete low-degree polynomial inequality, then it's very likely that, at least in an approximate sense, it's captured by the sum of squares knowledge. And that means that and that sort of means that, in some sense, if you work with these, if you work with a pseudo distribution that is consistent with this kind of sum of squares knowledge, and you're thinking about algorithms that try to extract a good solution from a pseudo distribution, it's very hard for them to notice the difference between having just a pseudo distribution and having an actual distribution. Just because our sort real-world knowledge about low-degree polynomials is very captured by this kind of sum of squares knowledge. And so this informs the following some kind of algorithm design approach. An approach for solving this problem, for extracting a good solution. So analyze this rounding step. While pretending, pretending that we have an actual distribution. Let's say low degree moments of an actual distribution. And then, only afterwards, check that that only sum of squares knowledge, low degree sum of squares knowledge, was used about the solutions. Okay, and this has the advantage that somehow this verification is can be technically involved, and somehow in dealing with it separately makes things much cleaner, or at least easier. Okay. Do you have, say, 5 more minutes? Sure. Okay. So I just wanted to sketch just how you can use the pseudo distributions to create, to design algorithms. It's not it's the example is chosen so that it's familiar, but you could, for this particular example, you could also do it in a different way, which might be simpler and depending on your taste. And this will be, suppose we try to approximation for max, try to get an approximation for max cut. Using pseudo distributions. Okay, so suppose that we have a graph G, and it has a bipartition with 1 minus epsilon fraction edges crossing. So 1 minus epsilon fraction of the edges of the graph cross this bipartition. And our goal is to find bipartition with 1 minus order root epsilon of the edges crossing. Okay, so how does the algorithm work? And that's the proof. So we'll, the first step will be that we compute, because we will compute a pseudo distribution. D that is consistent with let's say degree 2 with some squares knowledge, and the condition that the Laplacian is equal to 1 minus epsilon times the number of edges in the graph. So that just means that this fraction of edges cross. Okay, and now we want to extract from the pseudo distribution an actual distribution, an actual solution. And the way we can do this is, so I will explain why these steps work in a second. We sample a Gaussian, we sample some real valued random variable. Let's call it y. That has the same degree 2 moments as the pseudo distribution D. Okay. And then we will just output. So maybe let me just say this a bit differently. So if this pseudo distribution would be an actual distribution, what we'd like to do is just sample from this distribution. Okay. But as we said before, we only know the low degree moments of this distribution. And if you have, this in general, it's hard to sample from a distribution that has the same, even the moments. It's hard to sample from a distribution that has the same moments. But one thing that we can do is we can sample a real valued random variable that has the same degree 2 moments. Okay, and so all of these words are important. So it's a real valued random variable and it has the same degree 2 moments. That's something that we can do, and I'll explain why. And then we'll output the closest point, output the point z, which is coordinate-wise, we take the sign of the random variable y, and this is our bipartition. Okay, so this is the closest, closest point on the hypercube to the vector y. And so what I and then so there's one claim which will establish that you that you get this kind of guarantee is that if the probability under the pseudo distribution that xi is different from xj is equal to 1 minus epsilon, then the probability, which is now with respect to an actual distribution of z, that zi differs from zj, this will be at least 1 minus order root epsilon. Okay. Now what's sort of one step that is not so clear at this point maybe? Why can we sample a real valued random variable that has the same degree 2 moments as this pseudo distribution D? And so what we'll do is we will sample a Gaussian variable that has we will compute the degree 2, let's say the covariance of D. Okay, so what does the covariance mean? So we look at the following matrix. And this notation here is just it means exactly the same as here. So we use D to weigh these matrices. We get a new matrix, and we claim that this is so this will be we will try to choose we will sample a Gaussian that has this covariance matrix. And but for this, in order for this to be if you want to be able to do this, then this matrix needs to be positive semi-definite. Okay? So this is the main question. Okay? Why should this matrix be positive semi-definite? If this matrix is positive semi-definite, then you can choose just a Gaussian matrix with this covariance matrix, with this covariance. I'm sorry, mu here is the mean of the pseudo distribution. Okay, so why is this matrix positive semi-infinite? So if this would be an actual distribution, then it would just be a non-negative weighing of these matrices, of these PSD matrices. So it would be clearly PSD. But we have to, because it's a pseudo distribution, we have to we should verify it. And so now let's look at any vector u, and look at whether the quadratic form, if you plug in u, is non-negative. And now this pseudo expectation behaves exactly like you would expect from an actual expectation using this definition. And so this is the same as, so the value of this quadratic form is the same as the expectation of this square. Okay, so this identity would be true if this would be an actual distribution, an actual expectation, but because we're just using linearity, this is also true for these pseudo expectations. And now, we see that this here is a square of a linear polynomial. Linear polynomial in X. And that means that it's in, that this here is contained in our, in our sum of squares, degree 2 sum of squares knowledge. And so it means that this is non-negative for every u, and that means that the matrix is positive semi. Okay, thanks. So let me just say, so in the next lecture I wanted to talk about limitations of these kind of algorithms and how you can use them to solve some unique games in sub-exponential time. And on Friday I wanted to talk about applications of this to finding sparse vectors in subspaces and tensor decompositions. Okay, thank you.
Since it's late, probably we'll take the questions offline.
Do you want to start the next talk 5 minutes?